solve it for you, but I'll solve it real quick. So when you toss a coin twice, you can just list out the things that can happen, right? Like we did the other day. Heads, 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 tails, tails, heads, tails, tails. Remember how we did that the other day? Those are the 4 things that can happen when you toss a coin twice. So what's the probability that at least one of the tosses will come up heads? Yeah, because 3 out of 4 of them have at least one head, don't they? 3 out of 4 have at least one head. So there we go. Easy enough? Make sense on that? All right. Well, without any delay. Okay. So there we go on number 6. So the answer's on the thing, but let me show you why. So I'm going to draw it one more time, the big bell curve. So now we're going to get all the details of the bell curve. So this is, make sure you get this down. This is going to be the most important thing for the next exam. The main thing you want on your card is this big old bell curve thing. Well, that wasn't very good. Draw yours a little better. A little more bellish. So let me try again. All right, that's as good as my drawing gets. All right, so in the middle, so you have the line in the middle and 3 lines to the right, 3 lines to the left. So 1, 2, 3 to the right. So here's the middle. And 1, 2, 3 to the left. So 3 to the right, 3 to the left. Okay. And then remember the percentages go in there. That's 34%. 34% on each side. 13.5% for each next section. And then 2.35. Move this a little bit. 2.35, 2.35, and then 0.15, 0.15, okay? And then on the bottom, go the percentage, the title. So this is mu in the middle, it's the middle, and then each line adds a standard deviation jump. So this is mu plus 1 sigma right here. This line is mu plus 2 sigma. And this line is mu plus 3 jumps to the right. And then as you go left, it's mu minus 1 jump. And then it's mu minus 2 jumps. Yeah, I'm running out of room here. So it'd be mu minus 2 jumps. And this one is mu minus 3 jumps. All right, so there we go. So copy that down. That's the main thing we're going to use for the rest of this chapter. We're just going to keep going back to that again and again and again and again and again. Let me explain to you the percentages are pretty clear to you. What it means on the bottom. What mu means the middle, means the average, right? So let me put this in a real life context. This is called the bell shape. It's called the bell curve for obvious reasons. It's called the Gaussian curve sometimes because Gauss came up with it. The Gaussian curve or the bell curve. Okay, what it means, it's the way pretty much everything happens naturally in the world. So, for example, if you were to pick anything, men's shoe sizes, for example, women's shoe sizes. Yeah, I'll just go with women. What's average women's shoe size? I have no idea. But maybe it's something like 8, 7? I'll say 7. All right. Let's just pretend average women's shoe size 7. That would be the middle. That's the average of all women, let's say. But then not everybody's average, right? Some have bigger feet, some have smaller feet, right? Well, how much? Well, some have way bigger, some have a little bigger, some have way smaller, some have a little smaller. Right, but what's the average distance from the middle? That's called standard deviation, right? Remember what standard deviation is, the feel of it? It's the standard or typical or average deviation, distance from normal, distance from average, distance from middle. So that's what the sigma is, that little squiggle O thing. That's what each of these lines is. Each of these lines is one normal amount off the middle. So let's say the average women's shoe size is 7, Let's say that's the mu for women's shoe size. And the sigma jump, like how much people are off the middle, women are off the middle typically, let's say 2. So this would be 9 then, right? I'm just taking 7, I'm going to add 2, add 2, add 2 for every line, because that's the sigma. I just made it up. They'll tell you in any problem what the middle is and what the jump is. They'll tell you. So I'm just going to add 2, add 2, add 2. And then the other way, I'm going to subtract 2, subtract 2, subtract 2. Now, what in the world would that mean? Real life, if that was the case, if the average women's shoe size was 7 and the standard deviation was 2, so the jump was 2 for every line to the right and 2 for every line to the left, that would mean that 34% of all women, see this section here has 34%, that would mean that 34% of all women have a shoe size between 7 and 9, for example. That's what that would mean. Right? And let's add this one. Now, 34 and 34, 68% of all women have a shoe size between 5 and 9, for example. That's what that would mean. Up here, only 0.15%, way less than 1%, right? 0.15% of all women have a shoe size bigger than 13. Probably true. Right? And way over here, only 0.15% of all women have a shoe size less than 1. Can you have that? I don't know. I mean, these numbers are sort of made up. But anyway, you get the idea, right? Those percentages would be the case for women's shoe sizes. But it's not just that. Pick anything you want naturally. Let's pick, come down here. What if I wanted to grab the oak trees out in some park, right? And take the average leaf weight. There'd be some average. If you grab all the leaves and weigh them all, there'd be some average. I don't know what it is. I'm going to make up numbers completely here. 12 something ounces. 12 ounces. Just guessing. So let's say the average leaf weight on oak trees is 12 ounces. Do oak trees have leaves? Yeah, they have leaves. Right? Yeah, oak leaves. So 12 ounces. And the standard jump, let's say it's 3. No, let's say it's... Well, here, let me make the average like 16 ounces. I'll change it. 16 ounces. The average will be 16. I'm just making this up as I go along here. I just want to give you the general feel. Let's say the average is 16. That means the middle is going to be 16. And the standard deviation, meaning the typical oak leaf, is off the middle by 3 ounces. That's what that means. Remember what standard deviation means? You got a feel for that, right? So if the typical oak leaf is 16 and the standard deviation is 3, that means not every oak leaf is exactly average. Some are bigger, some are smaller. Well, how much? Some are way bigger, some are a little bigger, some are way smaller, some are a little smaller. On average, the typical oak leaf is off the middle by 3 ounces. That's what that standard deviation of 3 means. Standard, typical deviation from the middle. So if that's the case, then 16 in the middle, add 3, add 3, add 3. Then the other way, subtract 3, subtract 3. That's a 10 there. Subtract 3, right? So that would mean that what? 68% of all oak leaves weigh between 13 and 19 ounces. Right? So notice how the percentages never change. Now, let me say that real clear a couple times. Everybody seeing that? From problem to problem to problem, the rest of this section and the next, the rest of the chapter, the percentages are always the same. Those never change. The numbers on the bottom change, depending on what you're measuring. Women's shoe size, men's heights, oak leaves weights, caterpillars widths, whatever. Real life phenomenon you're measuring. Almost, without exception, things turn out to flow in a bell-shaped curve. Meaning, whatever the average is, most things are average. Most, women's shoe sizes and men's heights and oak leaves weights are average. Whatever the average is, you get a big hump in the middle. That's what the bell curve is, a big hump in the middle, meaning most people or most characteristics are average. Now, can you get some really, really big oak leaves or really, really tiny oak leaves? Yeah, but it's not going to be often, right? It's much more rare. It comes down fast as you go to the extremes, right? If you're 3 standard deviations above the middle, you're way above average. You're 3 typical distances off the middle above or below. You're weird. You're real big or real small. You're way off the middle. You're not average at all. Does that make sense? So the percentages always remain the same. This is what Gauss discovered. This is what's been discovered in naturally occurring phenomenon. Same thing true if they give SAT tests, right, to all the high school kids that just graduated, right? I don't know. I haven't read the numbers, but I'm sure there's some average, there's some standard deviation, And once you put that down here, 68% of all the kids are in this zone, and a few are really high and a few are really low, you know. Same kind of thing. Whenever you have any naturally occurring phenomenon, you have a middle, an average, and then you have the dropping down in the bell curve. And the percentages are always the same. Well, that's what they mean when they say such and such data fits the bell curve, or fits, the other name, it's called normally, let me give you the other name. There's a lot of names. Normally distributed. Yeah, it says it up here, huh? Normal distribution. Yeah, so if they say da-da-da data is normally distributed, that means it does the normal thing. The normal thing is the bell curve. They mean those percentages are really close to accurate. They'll say approximately normally distributed. That's what you'll read that in literature. So I know, real life, you're not going to be asked to crank out a bell curve and stuff. But real life, you will read studies. In most professional jobs, you'll read a study in which they give numbers and they say such and such data was normally distributed, and this was the result of the standard deviation. And this will give you the context of what that even means, what they're even talking about. Normally distributed data, bell curve data, like things are normally distributed in real life phenomenon. Okay, now to the question. What's the question? They're saying this normally, so they're not telling me what these are down here. They're just saying there's some kind of normally distributed. The sigma, that's the jump amount, right? The jump, the standard deviation jump. The jump from line to line is 9.3. And 84% of the data, I can't read this up here, what does it say? Fall below 48.1 centimeters. Okay. Okay. The standard deviation jump, the amount from line to line here, the jump, is 9.3. And 84% of the data fall above 48.1 centimeters. Okay. Hold on for a minute. Now, if they say 84% of the data, so when they're talking percentages, we're looking at these numbers up in the top, right? Because that's where the percentages are. When they say the 48.1, guess where that's going to be? Somewhere down in the bottom, because that's not a percentage. You with me? Percentages up top, non-percentages down below. Okay, so with that in mind, I'm looking for 84% up here. Now, it's not just one section. It's a combo of several sections. How can I combine several of these percentages and get 84%? Let me help. This is the middle line, right? How much is all of this? Since it's everything to the right, it's half. So what is it? 50%. If you add up 34, 13.5, 2.3, 2.5, you get a half. You get 50%. Because it's half the curve, right? Does that make sense? So from the middle to the right, or the middle to the left, either way, it's 50%, right? And on top of it, what if I added one more section here? What's 50? What's half the curve? 50 plus 34 more. 84. There's the 84 they're talking about. They're talking about middle and one more section. That's how they're getting 84%. They're saying 84% of the data fall above. See those words right there? Fall above. So that means there's some mark right here, which is, what is it? 48.1? 48.1 right here. And 84% of the data is above it. Do you see how I determined that? Does that make sense? It must. How did I know it was left of the middle? Why didn't I go over here one jump to the right? Well, because above to the right is 84% of the data. More than half of the curve must be to the right. So I must be left of the middle if more than half the curve's to the right of me. Does that make sense? That makes sense? Right? So I must be left of the middle if 84%, that's more than half, right? If 84% is above me, is to the right of me. Above means to the right. Right? So I must be right here, and there's how much is above me? How much percentage is above me? 34, 34, 13.5, 235.15. If you add those up, it's going to be 84. How do I know? Because it's 34, and all the rest make 50. So it's 84%. Okay, so what? So 48.1 must be the first jump, the first line left of the middle. That's what they're telling me. They're saying blah, 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 48.1 is the first jump to the left of the middle. Okay, so what? Can I find the middle? How do I know? How big is the jumps? They told me, 9.3. So every jump from line to line to line to line in this data is 9.3. They're telling me. So take the 48.1 and add the 9.3 to get the middle spot right here, right? Because 9.3. So if you add that up, that's how I'm getting the 57.4. That's the middle. 57.4 right in the middle. Is that good? Are we happy about that? Is that okay? Questions? All right. Okay. So as soon as they talk about the normal curve, I'm just going to draw it again real quick. Not the whole thing, not all the detail, but just boom, middle, 3 lines to the right, 3 lines to the left. Here's the middle. 34, 13.5, 2.35, 0.15, 34, 13. You'll have this on your 3x5 card. Okay, so now what are they saying? What percent, this is the middle, mu, what percent of the data fall below mu plus sigma? Well, this is mu plus 1 sigma, right? It's one jump to the right of the middle. You with me? They're saying what percent of the data fall below, that means to the left. Below is left, above is right. Below is left, above is right. Below mu plus 1 jump. So, what percent of the data fall here? That's what they're saying. What percentage left of 1 jump to the right? Right? You see this mu plus sigma? That's really mu plus 1 sigma, isn't it? Since there's no other number there. So they're saying if you go mu plus 1 jump to the right, so you go 1 jump to the right, how much is below? See below? How much is left? What percentage is left of that? So what is all that percentage? Well, from here left is 50%, because it's half the curve. And this section's 34, so add them up. That's how I came up with the 84. Is that good? And then next question, what percent of the data fall between mu plus 2 jumps and mu plus 1 jump? So between in here, right? Because this is mu plus 2 jumps. So between mu plus 1 jump and 2 jumps, what percent of the data is right in here? Well, 13.5. Well, we're done with that question. They're just asking you to read that curve. It's all about that curve and understand what they're meaning on the bottom. Is that good? Questions I can answer on that? All right, I'll keep moving, but I don't want to go too fast, so let me know. Say, hold it, Mr. Harris. We did do all that last one. Yeah, that was everything. Okay. So, here we are again. So every one of these problems, you want to basically draw another normal curve. Just quick, just real quick. In the middle. And they're saying the middle's 12.4 on this one, huh? And that goes in the bottom. Percentages in the top, numbers in the bottom. So 1 jump to right, 2 jump, 3 jump to right, 1 left, 2 left, 3 left. And then each of the jumps is 3.1, isn't it? So that means I'm going to add 3.1. This will be what, 15.5? I added 3.1 and then add 3.1 again, what's that, 18.6. Add 3.1 again, what's that, 21.7. And then subtract 3.1, what's that, 9.3. And subtract 3.1, what's that, 6.2. And subtract 3.1, it would be 3.1. And the percentages never change. 34, 34, 13.5, 13.5, 2.35, 0.15. There we go. All right, we good so far? If I just drew the bell curve, the percentages are always the same. And I did the bottom because they gave me the middle, 12.4, and the jump amount, 3.1. So I just added 3.1 each time and subtracted 3.1 the other way. Now, here comes their question. What percent of the data is between 3.1 and 21.7? Well, here's 21.7. Here's 3.1. They want all these percentages, don't they? See that? So you can just add them all up on your calculator, or if you want to save time, you can just subtract the two parts that are missing from 100. Either way. Right? What are this little part's missing and this little part's missing? That's 0.15 and 0.15 adds up to 0.30. So this is what's missing is 0.30%. So 100 minus 0.30 is 99.7. There must be 99.7% of the curve. Almost all the curve is in the middle there because it's only missing the 0.15 and 0.15 and 0.30. Or you could have just added them up. It's quicker to subtract though. Does that make sense? We good with that? Once you draw the bell curve, it all makes sense, right? I hope. Things I can answer on that? We good with all that?
How do you get 99.7?
Yeah, so I'm taking 100.00 minus 0.30. Like $100 minus 30 cents be $99.70. Yeah, it's easy to miss that little point there, a little decimal. Yeah.
So how do you get the 3.1 on the bottom?
Oh, yeah, they told me right here that
Yeah.
the jump amount was 3.1. So that's the jump from line to line. So they gave me the middle, the mu's the middle, so I started at 12.4 in the middle. And then I just took that 12.4 number and I added 3.1, added 3.1, added 3. So that means, the sigma means how much you add from line to line. And to the left we subtract that amount from line to line. Is that good? And then I found that what they wanted, they said between 3.1 and 21.7. So I said, oh, they want from here to here. They want all the percentage between those two. So they wanted everything except the 0.15 and the 0.15. So I thought the easy way to go is take 100 minus what's missing. They're only missing 15 cents and 15 cents. I added those up to be 30 cents. Took $100 minus 30 cents, and I get $99.70. 99.7%. Is that all good? Any other questions on that one? Okay, good. So that's 16.1. Let's go. Okay, let me actually save.